will today concentrate on constructing small cancellation groups. Again, we look at a group which is given by generators and relators. As I recall, we assume that the set of relators is closed under cyclic permutations inverses. Actually, we look on this relator as second words. Then we assume that there is some additive measure on these cyclic words. So if U is a subword of the word R, then it can take values from 0 to 1. It's an additive measure of the relators. For each relator, the measure of the relator is 1. The measure of the empty subgroup will be 0. Then we introduce some constants. Look at this way. This will be 0, 1, half, and we add threshold tau. And now we will have two values, which is 0, lambda 0 and lambda 1. I will relate in a moment. And then we look for the small cancellation condition, which involves some constant epsilon bigger than 0. The small cancellation condition means that if we have two relators which have a common piece, for example, let this be S1, S2, and S3. If S2 is not graphically equal to S3, then the measure in both of them of S1 is less or equal than epsilon. It could be if we have a relator R1 and a relator R1 and relator R2. So both R1 and R2 measures of this common part will be less than equal than epsilon. And this is our small cancellation condition. Assume that sigma 2 and sigma 3, S2 and S3 are different words. Okay, and then the common part should be less than equal epsilon. We look on epsilon as a small constant. Actually, until the end of this course, we will not try to make our constants as good as possible. Actually, it could be done, but we will not pursue this. So just think of epsilon as a very small thing, something 1 to 100, doesn't matter. Okay. Please.
How do we define the measure?
In some way.
Is it the same measure for both of them?
No. I stress it that it is a personal measure for each relator. The simplest way it could be done will be the relative length. But this is not the only measure we're going to use. Just any measure which is additive gives measure 1 to the whole word and gives 0 to the empty word. There may be some mild additional conditions. Okay. And then we are trying to, yes, of course, we will assume that these distances are, so tau is much bigger than 0, much less than 1/2 is a threshold. Half is much less than lambda 1 much less than lambda 0 much less than 1, for example, in terms of epsilon naming. For example, we will assume that 1 minus number 0 is bigger than tau plus 2 epsilon. So this is far enough, so lambda 0 is far enough from 1, in the same way, lambda 1 minus lambda 0 is bigger than 2 epsilon, lambda 1 minus 1 is bigger than 2 epsilon, maybe much more than this last method. So and tau is bigger than 2 epsilon, etc. So with all these constants set. Now we introduce the class of lambda semi-canonical words. The word W is lambda semi-canonical. We will write it as W S semi-canonical of lambda. If W does not contain subwords W equal A S B with S a subword of a relator R our relators with L R of S greater or equal than lambda. So we consider the set of forbidden words. Forbidden words are subrelators such that their length, their measurable length function, whatever you call it, is bigger or equal than lambda. Lambda is any number. I didn't fix it. It could be lambda 0, lambda 1, etc. for any value. So this is depending, this definition is depending on the parameter lambda. So it's lambda semi-canonical if it does not contain this type of forbidden words, subwords with lengths, with measure of bigger or equal to lambda. So this we introduce this class of semi-canonical words. Now, by a list of forbidden words. This class is defined by a list of canonical words. So we are going to define the following things. One, a certain equivalence on the set. Actually, we will take lambda 1 semi-canonical words, we will define a equivalence relation. We will define a product, and we will show that it is stable under this equivalence relation, and we will show that therefore it could be defined on the set of equivalence classes, and we will show that this product is associative. And then it will be easy to show that actually this group of equivalence classes under this multiplication is isomorphic to our original group. So this is the route we are going to construct small cancellation groups. So the first thing that we should do is to define the equivalence for two lambda semi. Actually, we take two lambda 1 and lambda 2 should be two semi-canonical words for lambda 1. We should say when these words will be declared equivalent. This is our first task. Now, there actually could be different ways to do it. Yes, please.
How does this connect to the semi-canonical definition from last week?
It's the same.
So do we take one word and we take all the semi-canonical?
No, let me say it again. A word is semi-canonical if it does not contain forbidden words. What are the set of forbidden words? These are too big parts of relators. How I know they're too big? That their measure is bigger than equals to 1.
Because last week we defined it if it doesn't have x minus
Oh
1.
no, this was a toy example for the free group.
Oh, okay.
Now, here is a question whether we should take E greater or greater than equal. This is a matter of test, yes. So far, let us take it to equal. Or no, because actually, what is the meaning? It's forbidden, it's too big, right? So it should be this way. It exceeds something. We cannot, so much we cannot tolerate it, so it's much bigger than one. Technical doesn't matter. Okay. So, now a definition. Let me also recall that we have defined the notion of a term. A term means that if we have a word, W, we have its subword S, and R is related equal to ST, then if this is A, this is B, so we substitute S by the inverse of T. This we call a term. Actually, because R belongs to the set of relators, this we are called this is R term. This is in one term. Now, of course, when we perform an R term, so actually we have both words represent the same element in the group because R is a relator. Now, definition. W1, W2 in lambda 1 are equivalent if there exist words V1, V2, Vk in SC of lambda 0 and a sequence of R terms we say V0. W1 is equal to V0, V1, V2, Vk, which will be equal to W2. So we can reach W2 starting with W1 through a sequence of R terms subject to the condition that all intermediate words belong to SC of lambda 0. They are semi-canonical with a parameter lambda 0. And I also said that we have this condition that lambda 2 minus lambda 1 is bigger than 2. So this is now our original definition of equivalence of lambda 1 semi-canonical words. Let us see what we can get from this. Just to understand the situation, let me also recall the very important notion of an arc chart. So we look, for example, on the word W1 and we consider its arc chart. Its arc chart is the set of all maximal occurrences of subrelators subject to the condition that their measure should be bigger or equal than tau. Tau is our threshold. So we have what I mean by maximal subrelator. I mean this word itself is a subrelator, but if we add even one letter on the beginning of the end, this will not be any more a subrelator. Now, the previous time, we noticed that while there might be an overlap between the members of the chart, but it never happens that one member of the chart is properly contained in the other. It also doesn't happen that one is covered fully by all of his neighbors. So neither this situation nor this situation doesn't happen when epsilon is chosen small enough, and actually this is easy exercise how to find the constant that prevent the situation. Okay, yes?
I don't understand. So for example, if you take the relative length as a measure,
so
how can you have when you do an R term, so you will introduce. So, for example, if the measure of S is a third, then you will introduce a T whose measure is 2/3, right?
yes.
So,
Right,
then,
exactly,
so
yes.
then the result will not be semi-canonical anymore.
Oh yes.
So
Oh, so,
how
but
can you
by the way, this is a definition of a term, whatever the constants. This is just a definition. This is a term that we have a relator divided into parts and substitute one part of the other.
But no, I'm asking about the definition of equivalence.
Oh, now here we assume that we have a sequence of terms, but subject to the condition that all the intermediate words have these conditions. They belong to semi-canonical words with parameter lambda 0. So I don't allow such words in between that their subrelators should be bigger than the constant lambda 0. This is just a definition.
Okay, I just don't see. I can't think of an example where you would have a sequence which is longer than
Which?
2, which is longer than where k is greater than 2.
Why? Let us give an example.
Yeah.
So actually, so we have, for example, this one, and this. And assume that this was our chart. Now we perform, for example, this term, so we substitute this part by this part. Then we substitute this by this. And now, because now this is absent from this, so we have to take all of this, So this becomes smaller and this becomes greater, but the difference is less than epsilon. And here we perform another term. So the resulting word will be, if this was one W1, the resulting WB will be this way. This is W2. Okay? Is something that
This one is a semi-canonical?
we have to look at it. So, because there are many ways, no, we assumed that W1 and W2 are lambda one semi-canonical. There's equivalence between lambda semi-canonical bonds. So, if we will not look what we're doing, then there are many possible ways why W2 would not be semi-canonical. For example, if this would be too short, then this would be too big and give us a forbidden word. So actually, if we are succeeding to doing this, having W2 as well lambda 1 semi-canonical, it means that this part could not be too short. Otherwise, the other half will be too big.
But the measure of the whole blue circle should be 1.
Always, yes.
So then either the subword that you had in W1 was too long, or the subword that you replace it with is too long.
Let me see. Think of this lambda 0, lambda 1 as about 2/3. Okay. So when something plus minus 2/3. So it means what is too long for us, which is bigger than 2/3. Then, of course, there is no problem assuming that both sides are less than 2/3.
So you need to be bigger than half or something.
Yes, of course. Ideally, they're close to half, but it may be bigger. It may be 0. It may be 0.6 and the other 0.5, 4, etc. Whatever. And of course, here, what you see here is that when we performed one of the terms, then it has an influence on the R chart, because then it could be influenced in two ways. If there was an overlap, then the next R chart, this will be smaller as the original, but it's smaller no more than by epsilon, because the common part is an epsilon measure. Or it could be opposite. It could be that when we perform a turn, now it may happen that now this element of the chart become bigger, but also no more than one epsilon. So it could happen, it could go in two ways. When I am taking a turn, it may influence the measure of the neighboring elements of the chart. It could influence making it bigger or making it smaller, in both cases, no more than by epsilon. In any case, this definition tells us that we perform a number of such turns. All the in-between words should be bounded by the constant lambda 0. As I told, lambda 0 is a milder restriction than lambda 1, because it's a smaller set of forbidden words. But at the end, we return to W1, which is also semi-canonical with the parameter lambda 1. This is the definition. And now we will try to work out this definition.
So
yes.
So if you, so they have to cancel out in some way for both of them to be in lambda 1, right?
No,
Like if you have a sequence of like making the R chart bigger and bigger. Never mind.
No, let me explain what are the possibilities here. Actually, let me say, because of the conditions we impose on the constants, actually, so we will, when we start, we will, how these terms influence the chart. I'm claiming the simple thing that every element of a chart, which is length is at least tau plus 2 epsilon, will have its non-trivial image in the result. It's important. Let me state it. Explicitly. So, when we perform a turn, first, how does it affect the chart? For example, it might be that we had here an overlap. So we had this green one, it's substituted by its complement, and now this part of the chart is shorter. But maybe that its length was more or less tau before we performed the turn, and what happened after we performed it became tau minus epsilon. So it will be below our threshold. So it will disappear from the chart of the new world. But only it was already very short, but it was over the threshold. Now we shortened it by something like epsilon or less, and it disappeared because now it is below the threshold. This is one thing that could be. Opposite, it could appear, it was not present in the original chart, and it could appear in the new chart for the symmetric reason. So we had here some related, but it was not satisfying the threshold. Now we add something, and now it is now up to the threshold. So it will appear here, while it didn't appear in the previous one. So those elements of the chart that their length is close to tau within 2 epsilon, because this could happen for two sides of it, so they may appear or disappear. But all the others, when they are big enough, when they appear in the world before the turn, they will appear, better not them, their traces will appear in the world after the turn. Because anyway, it was bigger than tau plus 2 epsilon, even if it is shortened, it still is over the threshold, and the opposite, if it is in the resulting world more than tau plus 2 epsilon, so it was bigger than tau in the original world. So this is, as to say, a partial one-to-one correspondence, except for very short words. Now, the important point is here that when we perform a number of such terms, and then we have this resulting new world. When we try to perform the new term, I mean from V I minus 1 to Vi, so this term should take some subword of this word and take its complement. Now, because we know that the resulting word should belong to S say we come with lambda 1, so this length of t should be less of lambda 1, it should be less than lambda 1, therefore the length of S should be bigger or equal than 1 minus lambda 1. Or if you, no, here is lambda 0, we assume lambda 0, this is lambda 0. Lambda 0 is bigger than tau plus 2 epsilon. It means that this S could not be too short. If it would be short, then the term would take us outside the class of SC lambda 0. Now, but if we look element of the chart in the V I minus 1, its length is 1 minus lambda 0 at least, which is bigger than tau plus 2 epsilon, then it could not be a new element of the chart. It should be an element of the chart from, this is image of those that already exist. This is the reason of this, of this condition. Because then, because we have a new, so maybe we could take here on the border of this something new. So I mean, it could be, we might be afraid that we have to, then if we take such a thing, yes, but it could not be because this will be 2 epsilon, which will be too small for this, and then the complement will be too big. It means that during all this process, we perform turns only on such words that have a non-empty intersection with the original word W1. This is important, and it follows from this condition and what we impose on the constants. Therefore, we may say that what actually happens, we can describe now all this process in the following way. We have some elements of the chart, and then what we have done, in some order, we performed the turns, but only on these elements of the chart is already existing in the original word W1. We never perform something that is not, its trace is not in the original word. But then it is easy to see that the result does not depend on the order of which we perform these turns. Because we have here a set of turns, all of them have non-trivial intersection with the original word, the result does not depend, the result does not depend on the order of performing turns. Why? Actually, it is enough to show that it is true for 2 R-turns. We perform one, then the second, or vice versa. Now, here we have actually 3 possibilities. If these elements of the chart are far, not touching even, then it is fairly obvious. We do this and then this, or vice versa, we have the same point. The next case is that they may have a point that touches, but not overlap. Then what can happen that they may have a common part, maybe not, but they may have a common part. And then it's also obvious that when we perform in one order and another is the same result. Now it could be that these have an overlap. So this was this way, the other had a non-empty overlap. And then again, when we look if we perform this, and actually influenced this, and then so it made it smaller, but then this complement will regain this part, and we have this. So or we do the other order, we start with this, and then this is smaller, and then performing the turn here, we regain the same thing. So it is obvious that in this case as well, the final result does not depend on the order. And then we have one more possibility. Actually, we do not have. But if we take some board, we perform the turn, and then we perform the turn on this one. Then we just return to the original board. So this argument shows that no matter what the order of performing the arc turns, or even if we will do the same thing on the same place, so the result will be the same. There is
Would it be possible in the second case that when you the first, if you do red and green, the one was sorry, you do green and red, so the red part you obtain is in the C lambda 1 class. But
So-
then if you do the other case, it was too long to be in the right class.
oh, just a moment, will we do in the now? The point is, just a moment, let us do the check. Yes, so we know that. Okay, so what is the danger? That here, no, I don't know, actually, I had this one. Now, then I perform the green.
Yes.
What happens with the red? Red becomes bigger. Now, but this word still will be in the class semi-canonical of lambda 0. So and then we perform the red, and then we have this one. So the resulting word is just if we do first the red and then the green.
Could it be that if you just do first the red, you go out of the class C lambda 0?
No, because this original in the class C lambda 1. This one is above W1. This is my point. This why I only require it to them into the bigger class. Because then this could increase by 2 epsilon, but because we require that lambda 0 minus lambda 1 is bigger than 2 epsilon, therefore all the intermediate results will be into the class of lambda 0 semi-canonical parts. It's important. Okay. So, but actually we have here two types of this, how these cells might behave. Or they may just have here a common part, or it may switch the side. So the result may just be of this type, is on one side of the W1, or it may switch the sides if we have this type of intersection. So, now, in any case, what we see here, that between W1 and W2, we have one layer situation. This is important. So there is nothing that is isolated from W1. All these are just in one row. All these touch both of these rows, W1 and W2. But it may happen that we have this situation. So in order to make it graphically easier, we just look in the following way. We have just this idea of a one layer map. We have one cells, maybe here several times. It may be just a point intersection, whatever. Now, and then in this one, the original W1 might go, it might switch sizes. And the other word may be going in a completely different way, doesn't matter. Choosing each time one side of this. So, but here, actually, okay. So it means that when we have this kind of equivalence, so we have this one layer map, and each of these words is inside this one layer map. Now, just it crosses this map, maybe switching sizes at will. Now, then when we assume that both of them belong to the class semi-canonical with the parameter lambda 1, so for them, each of the elements of the chart is no longer than lambda 1. But if we will go through this chart in some arbitrary way, then then of course all the sides here we can assume that all the sides on the also satisfy the same condition. I mean the condition of lambda 1 in this map, because if they doesn't contain, we can just remove them without harm. Because no one of these, no W1 and W2 will cross them, because they are subject to this condition. But nevertheless, any path that goes here will be subject to the condition SC of lambda 1 plus 2 epsilon. Because in any case, here it have no bigger than lambda 1 and two parts which each of them is no bigger than epsilon. So in any case, this will be. So this means that this applies also to all these V1 to Vk. One closing remark now, that when we originally defined this equivalence, it was dependent on two parameters, lambda 1 and lambda 0. In fact, it turns out it's depending only on lambda 1. Because while these V's are allowed to belong to the bigger class lambda 0, in practice, they cannot be bigger than lambda 1 plus 2 epsilon, because they must go as passes into this one layer map. So actually depends only on lambda 1 and doesn't depend on lambda 0. So let me stop at this point.